So this is a project that I've been working on off and on for a long time, and it's always fun to talk about the latest version of what we're doing. If I can get the right one. There we go. So I'm going to talk about the motivation for putting out new versions of these very widely used numerical linear algebra libraries, LAPACK and ScaLAPACK. Talk about the challenges we have or the research opportunities, and as you'll see, they're not just for high-performance computing, they're for everybody's computing that these challenges arise. I'll talk about the goals of this project, what we're going to do better, faster, more accurately than we did before, and then give you some highlights of the progress. It's a very large project with many collaborators, and so I'll just pick a few highlights to talk about. And I will permit myself some excursions into closely related topics like group representation theory, but you'll see why that's closely related. So a little motivation. These are widely used libraries. They're the basis of the math libraries of all these different companies and so forth. And I have no idea who, but there are 35,000 hits a day on NetLib to access these things. So they're certainly worth improving. And besides those industrial activities, it is also used to do big science. So here's an example of a cover of Nature where the question was, which theory of the universe is the measured cosmic microwave background radiation consistent with? The question is the universe going to expand forever more rapidly? Is it going to expand perhaps more slowly, or will it eventually collapse on itself in a new Big Bang? And by doing a 100,000 by 100,000 dense linear system using ScaLAPACK, they determined that the data is currently consistent with the universe expanding forever, however slowing down somewhat. Now, what is the practical implication of a result like this? Well, one could hope that eventually it'll moderate real estate prices in Berkeley, but I think that's probably a long-term effect. So eventually, this is a part of a large international consortium, and they're putting up a new set of satellites to collect further data because the error bars are pretty big on this computation. And when the Planck satellite goes up in 2011, they'll have 100 million by 100 million dense matrices in order to solve this problem. Now, they're hoping to have non-dense algorithms by that time, but in the meantime, this is the best they can do. So there are many ways to improve on these libraries, including our own algorithmic research. There's a lot of people around the world who are enthusiastic contributors and participants to this public domain library. People publish papers that say, I have a new algorithm and it's faster than LAPACK. We want to harvest all of that activity. And so many people have signed up to do that. We've done a user and a vendor survey of some of the largest users in order to set priorities of what we want to do. And new architectures, new programming languages all offer opportunities and challenges that we want to meet. And we do have some support, NSF support for a new release. Our next release will hopefully be in about a month. But as you can see, our agenda is much larger than we have support for, and so, which is why we're happy to have all our partners. So here's the list of participants. There's Berkeley and Tennessee. My colleague Jack Dongera is the other co-PI in this project, and we have our teams at our respective sites. But you can see here, you can see here, get the buttons right, that there's a lot of US and other universities where people are participating in contributing code, also research institutions and various industrial partners. Okay, so let me talk about the challenges now. And these are challenges for all large-scale scientific computing, not just linear algebra. So here's a picture of the 500 largest machines in the world from 1993 to the year 2005, categorized by how many processors they had. And so, for example, if you look down here, if you look down here, this says that in 1993, 100 of the 500 largest machines still had only one processor. They died out by 1996. And only a few, if you look at the red band, only a few of the largest machines had up to 256 processors. Up to 2005, only a few of the smallest machines have 256 processors. So parallelism is growing rapidly. And of course, BlueGene-L is up there with 131,000. So our algorithms do not scale this well yet. This is one of the challenges we have. The other example of large-scale computing is your laptop, right? So this does not sound like it's the same problem, but it is. Because all of the prognostications are that your laptop and everybody's laptop and your desktop will have 256 processors in it within 4 years. If you talk to people at Intel, some of them are more ambitious and they say 1,000 processors are going to be everybody's computing engine in that period of time. This is going to change everything, not just high performance computing, but everybody's problem is going to become large scale parallelism. And so we're sort of first in line to figure this out, and we're going to try to do that. So the other challenges are the costs of all these different algorithms are changing exponentially. We're kind of familiar with the idea that floating point arithmetic is the cheapest thing to do, and that's a whole lot less than the time taken to fetch words from memory. And that's a whole lot less than the time it takes for that first word to arrive. But in fact, these costs are changing exponentially apart. This is improving 59% a year, this is 23% a year, and this is 5.5% a year. So if you haven't, that means if you have an algorithm today which runs efficiently because it kind of does just enough floating point to balance, to hide all the memory accesses, it won't be good enough in 4 years because of this exponential change in costs. We have to fix that. The same thing is true with parallelism. Again, the network bandwidth is a lot slower than the floating point time, and the network latency is a lot worse. And again, you have these exponentially changing costs. And so in fact, something that scales well this year won't scale well in 5 years because of these problems. This 15% a year number is a little bit of a lie. It's gotten by drawing a straight line through clouds of data, of course. But in fact, between 1995, when the Cray T3E came out, in 2005, there was no improvement in network latency whatsoever. That was the fastest machine for 10 years. And so this is a problem that's going to be with us. And finally, these problems are going to come up with when machines become large. They're going to be heterogeneous. I think Los Alamos National Lab just decided to buy a large cluster consisting of opterons and cell processors. They don't even agree on the endianness of the word storage. So you move a word from one processor to another, that doesn't make any sense at all. That's about as heterogeneous as you can get. We're already used to that on our laptops with SSEs and regular old processors. It's only going to get worse with GPUs. Asynchronicity and unreliability of all this on very large machines is going to become critical. So these are all the challenges that make our lives fun and keep us getting funded to work on this. So let me just say a few more words about a user survey we did. This is a few of the largest DOE users who use large-scale dense linear algebra. We asked them, what do you need in the future? And so it's a small sample compared to the other users of MATLAB and so forth. But what matrix sizes do you care about? There's 26% of them who are up in the millions, who really want to do this stuff. There's about 20% of them over 1,000, but I think that's going to grow dramatically because of the DOE petascale initiative. We're all going to have these folks are going to have petascale machines in a few years with, well, up to 1 million processors, depending on whose architecture it is. Some of them need more than double precision fairly often, so the usual double precision will not be enough to solve their problems. And I'll come back to this later. Some of them want memory allocation and some don't. That makes a big difference in the design. So this is sort of the boundary conditions of all the design decisions that we're going to be making. Okay, so finally, what are our goals? We have 6 of them, but time permitting, I will only talk about the first 3. Better algorithms, of course, that's what I personally like to do. Faster ones and more accurate, so I'll give you some highlights of what those look like. Expanding the contents, there are a lot of algorithms we have not yet parallelized, a very large number of them. So ScaLAPACK, if you like, is a small subset of LAPACK and what it can do, and that's an issue. And finally, as you'll see, there's an awful lot of tuning parameters that we have never tuned before, and we need to automate that process because the best algorithm for one platform will differ dramatically depending on these tuning parameters from another. It's too much to do by hand, we have to automate it. And I understand there's a bunch of activity on that here too that I'll refer to later. Okay, so let's talk about better algorithms. There are 2 metrics of better, faster and more accurate. It's pretty unusual that you can get both at the same time, and so we're going to make the improvements when we can. Faster, but provide the usual accuracy and stability. We're not willing to sacrifice that. Or maybe it's only, well, maybe it's always faster, but maybe it's only accurate for some important subclass that we're willing to live with. So we'll identify a few of those cases. More accurate, but we'll insist on the usual speed so that the user doesn't have to wait a lot longer. But there are a few people who want the right answer at any cost, and we have to make them happy as well. So these are the different design points we're going to be adding stuff for. Okay, so here are my favorite top pick of the 5 best innovations for speed in here, and I'll talk about each one of these in more detail. Here's just an outline. The first one is the winner of the 2006 Siam Prize for linear algebra. It's work started a number of years ago by my colleague Parlett and our student Dylan, who's now at Texas, and a whole bunch of other people. It's an order n² algorithm for the symmetric eigenvalue problem. This is a problem you're given a tridiagonal matrix, symmetric tridiagonal matrix. You want all the eigenvalues and all the eigenvectors. In other words, the output has size n². And this costs order n², and it's embarrassingly parallel. It's we call it the holy grail, because it has everything you could want. Perfect output complexity and embarrassing parallelism. So that's going to go in there. The next improvement is for the non-symmetric eigenvalue problem. So if you have a large non-symmetric matrix, how do you find its eigenvalues? You first reduce it to something called Hessenberg form. I don't have a whiteboard, that's okay. Upper triangular plus one more diagonal. And then you iterate on that upper Hessenberg matrix. That's the bottleneck. And there's an algorithm that's up to 10 times faster for doing that. And in fact, that won the 2003 SIAM Linear Algebra Prize to make that work. That's Ralph Byers. So combining that with faster reduction to Hessenberg form makes the overall algorithm significantly faster. So I'll go into some detail on that. There are extensions of that to the generalized non-symmetric eigenvalue problem, not just finding the eigenvalues of one matrix, AX equals lambda x, but of two matrices, AX equals lambda BX. And that's work from collaborators in Sweden. And then finally, we're going to abandon, for some algorithms, the usual layout of a matrix. I mean, what's a matrix? Store it by rows, store it by columns. We're not going to do that anymore. We're going to store it in recursive blocks using space-filling curves, because that turns out to make it go faster on a certain number of platforms. So I'm going to give you a little bit more detail about each of these now. So as I said, I'll start with the order n squared symmetric tridiagonal eigenvalue problem, which won the SIAM prize. We had a version out in the LAPACK 3.0. It was wrong. We're fixing it. This new one is much better. I'll do the comparison, and we're going to have this much better version out in the next release. So let me give you sort of some performance numbers here and give you a tour. So I'm going to compare it to all the other algorithms. So we have a database of realistic matrices of sizes ranging from 50 up to 10 to the fourth. And what I'm going to plot on the vertical axis is the flop count. And so I'm going to start with the old workhorse, the QR algorithm, which has been around for a very long time. And so what I've done here is I've run the QR algorithm in all these test matrices. I've plotted the flop count. I get these blue plus signs, and I draw a straight line through it. And the slope of that straight line is 3. And that's because it's an order n cubed algorithm. So this just tells us what we already know. Let me add bisection and inverse iteration. This is another old algorithm that's been in there for a while. I again draw a bunch of points, put a straight line through it. Its slope is 2.9. Now this is a bit of a cloud of data. Sometimes the algorithm is more like n squared depending on the distribution of eigenvalues, but overall it's still basically an n to the cubed or an n to the 2.9 algorithm. There's divide and conquer, which has been the fastest algorithm for a while. It is also an n to the, it's not quite n cubed, but it's n to the 2.8, but it certainly is getting better. And then finally, here's the flop count for the new algorithm. And if you insist on drawing a straight line through that cloud of data, it's n to the 2.2. All right, not n squared, but it comes pretty close to meeting its design goal. Now that is a pretty cluttered plot. So let me instead normalize it by dividing by the flop count of the new algorithm. So it'll tell you how many more or less it does. So here, this is the flop count normalized to 1 of the new algorithm. This tells you how many times as many flops the other algorithms do. And you can see that with a few exceptions, where the old divide and conquer does something called deflation and runs about twice as fast, the other ones are 10 times as many flops, 100 times as many flops, 300 times as many flops. So this all looks good, but you're probably saying, is this guy trying to hide something? Why is he showing flop counts instead of runtime, right? The bottom line is runtime. So let me just change the axis and make it runtime. And here's the runtime ratios. And it's almost a win. It's almost a good thing to do. So it turns out that we still are 10 to 100 to something times faster than these old algorithms, but for divide and conquer, which are the red circles, it's a bit of a toss-up. Sometimes we're 12 times faster, and sometimes we're 5 times slower. And so what is going on here? The flops are dramatically better for the new algorithm, but the runtime is not. Let me just show a picture. And so here is the megaflop rate. I mean, the difference between flop count and runtime is megaflop rate. So let's try to understand what's going on inside these algorithms. So now I've plotted the megaflop rates. And I'm going to just look on this side, which is where things don't fit in cache, so I don't have cache effects. Here, QR is a nice flat megaflop rate. And when it falls out of cache, it's a little bit slower. Bisection inverse iteration is a little bit slower, but has a nice flat megaflop rate. Divide and conquer has an increasing megaflop rate. So the larger the problem, the absolute speed, it runs faster. So how could that be? Anybody have an idea of how you could run a larger problem and the megaflop rate keeps increasing? In this algorithm, what happens is it spends a larger and larger fraction of its time doing dense matrix multiplies as the problem gets larger and larger BLAS 3. And so eventually this thing is going to approach the speed of gem, of dgem, of matrix multiply. And it hasn't reached it yet. Down here at the bottom is our best algorithm that does the fewest flops running at a significantly slower megaflop rate. The story is, of all these algorithms, this is the only one where a fixed fraction of the work is in divides. So it does the fewest floating point operations, but a fixed fraction of them is divides, and divides are significantly slower than all the others. For all of these algorithms, they do negligibly few divides compared to everything else. So it's a win, but this is the story. So we thought about that and decided, well, is there something that we can do differently to exploit the new architectures that are coming along? And so we thought about graphical processing units, GPUs. Not just GPUs, because there are a lot of these other processors are on cell. We've put a lot of time into cell. The SSE2 units, grape boards, GPUs, physics coprocessors for Game Boys. There's a lot of these things coming out, and a lot of people have been asking, can we exploit them? And they've actually proven to be very little help if memory is the bottleneck. And there's a bunch of people, for example, at Stanford who've been working on this. However, this algorithm maps very well. You can fit the entire thing into a GPU memory because the data structure is not a big dense matrix. It's just a small tridiagonal matrix. And the inner loop turns out to map very well, even though there are a lot of divides. And there are speedups of up to a factor of 100 on running this thing on a GPU. And we actually got up to a 43 gigaflops on a game processor running this particular algorithm. So I don't think we have to worry about those divides in this environment where you have game processors. And we're still working on this because we've only gotten part of it to run on a GPU. We're still working on getting the whole eigenvalue and eigenvector algorithm to run on a GPU. So I'll say more about the cell in a little bit. Okay, here we have parallelism. This is going to come out in the ScaLAPACK version 2. All 4 algorithms, QR, bisection, divide and conquer, MR cubed, runtime as a function of the number of processors. Perfect speed up would be a nice straight line which is dotted. And we are scaling nearly perfectly after an initial slowdown. And so this is indeed going to be the winning algorithm. It beats divide and conquer. This algorithm scales well, but it gets the wrong answer. So that's too bad. But we can always go faster if we're willing to get the wrong answer. So I had a meeting at Livermore the other day with QBox. That's the world's fastest code for doing DFT calculations, density functional theory. It's run at 200 teraflops on a blue gene. Their bottleneck is this algorithm. So I'm looking forward to a new customer to getting this stuff to run fast. Okay, this is a little too busy, but we had a version of this before. The errors of the old algorithm are shown in triangles. The errors of the new algorithms are shown in the black diamonds. The old algorithm had a bug. So I apologize. It's been out there for a while. We're up to 1,000 times more accurate. But well, anyway, so it's all fixed now. Okay, so to summary there, numerical evidence shows that this is the best algorithm, except sometimes divide and conquer is faster if it has this property called deflation. We can't predict it in advance. We're going to keep both algorithms in there, and the user is simply going to have to choose. There is still an important numerical open problem here. The singular value decomposition is very closely related to this eigenvalue problem, but we haven't been able to figure out how to make the algorithm work stably on the singular value decomposition. That remains an open problem. We thought it was fixed. We found a problem, and so that's still open. Okay, so that's enough on that algorithm. Let me move on to the non-symmetric eigenvalue problem. This, as I said, won a SIAM prize also in the year 2003. We're going to have this version of the code out in 2006. Ralph Byers spent a sabbatical at Berkeley, and he spent the whole time hacking this code. He was very generous with his time, so that's why it's getting into the library. And I'll have performance in just a moment. It's up to 10 times faster, but I'll give you some performance data. Now, the whole non-symmetric eigenvalue problem combines this, which is the bottleneck, with this phase, which is reduction from dense to Hessenberg. And if you put everything together on a relatively small matrix, the entire process is now running that much faster. HQR, Ralph's contribution, is 5 times faster. The reduction is still a little piece of the time. It's 14% faster. And here's the performance plots. So if you don't want any eigenvectors and the time is normalized to 1, this is how much time the new algorithm takes. At 300 by 300, it's not much faster. It runs in 0.9 times as fast, but it's 3 times faster by the time you get up to 1500. And it's even better if you want all the vectors. So this is the performance improvement. It improves as the problems get larger and larger. Okay, in addition to faster Hessenberg reduction, there's also improvements in the symmetric eigenvalue code. So for example, if you want the singular value decomposition, singular values only, that'll go about 30% faster. Not as big an improvement, but there is still something there. Okay, and this is also extending to the QZ algorithm. And there, the speedups are even more dramatic. They're up to a factor of 12 by putting in Ralph Byers' new improvements. And 4.4 on average. Let me skip this slide. Okay, and finally, the last big improvement that in speed is to abandon the usual way of storing matrices, which is store the rows consecutively, store the columns consecutively, and to do it with space filling curves instead. So let me just sort of draw a picture to indicate how this works. So here, the idea of storing this matrix with a space filling curve is you store first, the Z shape says at first I store the northwest corner, then the northeast corner, then the southwest corner, then the southeast corner. So how do I store the northwest corner? I store it the same way. I break it into 4 corners and store them in the same pattern. How do I store that corner? Same pattern. And the whole thing just happens recursively. I could do it with a Z shape, I could do it with a U shape, or I could do it with some funny diamond shape. So that's the order in which the matrix entries would be stored, down to some block size. I mean, this is not necessarily a 1-by-1 matrix. It may be a 100-by-100 matrix, whatever fits in your local cache. So why is this a good idea? It certainly complicates, you can imagine what the indexing looks like. It's because, from the cache's point of view, as soon as you grab a piece of the matrix, the hardware naturally grabs all the other stuff that's stored nearby it. And so it naturally blocks the algorithm so that you have maximized the data locality without having to have lots of complicated loop indices and blocking. And it does a lot of what we have had done by hand before in Atlas and other kinds of tuning automatically. And people, this has been proposed by people like the Silk group, Charles Lysis at MIT. It actually only makes sense in the dense linear algebra world if you do not go all the way down to 1-by-1 matrices. You spend all your time in overhead instead. But this will also go into the next release. For some, and the best speedups are for not for everything, but it's for packed symmetric storage of matrices. Okay, so that's all I wanted to say about making algorithms go faster. I'm going to move on now to more accurate algorithms and getting a better answer. And there are going to be 3 highlights here. The first one is iterative refinement for solving AX equal B or least squares. And the goal there is we're going to promise you the right answer. I have to put promises in quotes because of lawyers and stuff. We don't have a proof. So promise the right answer for order n squared extra work. We're going to guarantee that the error bound is very small. And without interval arithmetic or any of the techniques that are usually used in that world. I'll spend most of my time on that. I'll talk about a new SVD algorithm that can be much more accurate. Jacobi has been around for a very long time, since I think 1846. It's always been the slowest algorithm too, so people haven't paid much attention. But it turns out that by suitable preconditioning, it's actually faster than the traditional QR algorithm now. And because of its accuracy, we're going to put it in. And finally, because there's some people for whom double is not enough, we're going to produce arbitrary precision versions of everything, and using appropriate modular techniques. Okay, so let me say a little bit more about the first one. And so we're going to promise the right answer. It's going to cost you an extra n squared work on top of the n cubed you're used to paying. It's going to do iterative refinement, Newton's method if you like, with extra precise residuals. So that means if your input is double, you have to compute residuals, ax minus b, to quad. We've produced a portable package that does quad on any platform using double-double. That's going to be part of the release as well. So let me show you a picture to try to indicate what errors you can expect. So I'm going to show you the errors from the traditional algorithm and then the new algorithm. So we took about 6 million 100 by 100 matrices. For each one, we computed its condition number. We solved ax equal b, and we computed the error. And so for each one of these, we took that matrix, and it corresponds to a pixel in this 2-dimensional histogram. So all the matrices in each bin are the number of matrices with a particular condition number and a particular error. And the bins are color-coded by how many matrices landed in that bin. So the darkest bins are the fullest ones, where most matrices are. They lie along this little narrow ridge. There are about 10,000 matrices in each one. So almost all the matrices lie on a straight line. There are a few up here, and there are a few down here. What this says, since that's a straight line, the error is proportional to the condition number, which is what we traditionally teach. This says statistically, sometimes you do better than that. Sometimes the error is better than condition number times epsilon, and sometimes a little worse, but not much. This line here is machine epsilon. You hardly ever get below that. And this vertical line is 1 over epsilon. And we know that when the condition number is larger than 1 over epsilon, you expect no accuracy whatsoever. So out here, the error is just awful. The log base 10 of the error is 0. It's order 1 error, so just rubbish. So here's what the new algorithm delivers. If the condition number is less than this 1 over epsilon, you simply get the right answer. It's less than machine epsilon, and that's the promise. And if it's larger, then it often works, but occasionally it fails, and we make no promises. So what the code will do is it will run iterative refinement. It will estimate the condition number. It'll decide, are you on that side or are you on that side? If you're on this side, it says, I promise you got the right answer. And that's the semantics. So the guarantee, as I said, is based on estimating the condition number. Is it smaller than 1 over epsilon, or is it bigger than 1 over epsilon? And to do that, and to have it all cost order n squared, we don't want to pay for this. We need to have a condition estimator that computes this condition estimator. It has to be reliable. And it can't lie and say you're on the wrong side of that vertical line. And in 6.2 million tests, it never lied. Now, does that mean we can trust it, right? Not from a mathematician's point of view, but let me just pursue this. Could that condition estimator possibly lie to us and tell us we have the right answer when in fact it is wrong? Okay, so here is a proof by picture, and then I'll say a little bit more about it. So what we did is we took those 6 million matrices, and we computed the condition number once the cheap way, order n squared, and once very carefully in double to get the truth. And then for each of those matrices, we made a two-dimensional histogram again, comparing the estimated condition number to the true one. Now, if they always agreed, all these pixels would lie on the diagonal. The two condition numbers would be equal. Now, occasionally, up here, so in this range, as long as the condition number is less than about 1 over epsilon, the estimated condition number underestimates the true one by at most a factor of 10. So we get the answer within a factor of 10. Up here, no guarantees. The condition number is very, very large. It could be we could very badly overestimate it or underestimate it, but both condition numbers agree it's large. That's all we care about. You're on the correct side of the line. So it can the condition estimator can lie to you awfully badly, but it's so large we don't care anymore. Now, this actually, if I get this to work. So the answer is yes, condition estimators can lie. In fact, I have a theorem that says a condition estimator has to lie. There have to exist counterexamples to any condition estimator unless the cost of it is as much as matrix multiply. The cost of condition estimate, the cost which is the same as the cost of LU factorization, which is a complexity theory result. You can provably produce a counterexample, and that's a theorem we published a few years ago. So, but it turns out that in practice this is not a problem because it can only lie to you when both answers are very large, which is all that we care about. So this says that if we actually wanted a mathematical proof, we couldn't do it for order n squared. We'd have to spend as much as matrix multiply. But how much does matrix multiply cost? What if it only cost order n squared? I will come back to that possibility at the end of the talk, that matrix multiply might now only cost n squared instead of n cubed or whatever the world's record is. Okay, so just to finish that, we're going to guarantee the error bound. We're actually going to get tiny component-wise error bounds too. Each component will have an error bound for it. The small ones will be just as accurate as the large ones. We're going to make it work for least squares problems, and this will also come out in 2006. Okay, just a few words about Jacobi. For many years, it was only a curiosity, because yes, it was more accurate, but it was so slow nobody paid attention. But my colleagues in Croatia, Zlatko Dormac, has now made it even faster than QR. So it's twice as fast as the traditional QR algorithm and arbitrarily more accurate. That will go in the library. And we're also going to produce arbitrary precision versions of everything using Fortran 95 modules. I could talk for a long time about the software engineering, but I won't. I'll just simply say that you can link in your favorite arbitrary precision package. We're going to be agnostic on which one because there's so many, and you can run to arbitrary precision and all these things. Okay, let me come back to cell processors, which are exciting. And as I said, Los Alamos is going to spend $100 million on a cluster with using these things. I'm not sure that's a good use of taxpayers' money, but anyway, that's the plan. One of the interesting things about cell is that it does single precision 10 times faster than double precision. And so if you were willing to run your code entirely in single, there's a factor of 10 there, right? A factor of 10 is interesting. And in fact, we're used to this. If you run on a Pentium with an SSE2, single runs twice as fast as double. So this has been around for a while. But a factor of 10 is something to pay attention to. So here's the idea. Given AX equal B in double precision, you want the answer in double precision, but I want to go 10 times faster. How do I do it? The answer is, if the condition number is small enough, factor it in single and do the refinement in double. So you do the n cubed work of factorization in single, use that as a preconditioner, and solve the problem in double. And the n squared part runs slowly, the n cubed part runs fast, and you get factors of speedup of 8 on the cell processor. For this important class of problems, it doesn't run on every double precision matrix, obviously, but for the important class where the condition number is less than this, then it works perfectly fine. If you take the same algorithm and put it on your Intel-based laptop, you get speedups of a factor of 2, because that's also the difference in speed between single and double. Right now, this is a sort of a curiosity. We're not sure if we want to make this generally available because, well, the semantics are getting complicated. But anyway, it is an idea. The idea applies to many algorithms. As long as you can, if this difference of factor of 10 is large, we could change all the algorithms in dense linear algebra to do something in single and refine in double. But we're hoping that the people at Sony and IBM and company will get rid of this factor of 10. It wouldn't take a very large change to the hardware, but whether they do that or not, we don't know. Okay, so that's the end of goal 1. And so what I want to do is talk a little bit about goal 2, which is to expand the content. And there's, right now, ScaLAPACK, the parallel version, is a small subset of LAPACK. And so this next table is simply going to show you, if you do an inventory, what I've done here is for each particular class of problems, linear equations, least squares, generalized least squares, there's a whole bunch of different problems that are solved. There are a lot of routines in LAPACK, and most of them are missing in ScaLAPACK, simply because the software engineering of producing this was simply too difficult at the time that we did it. And so, we don't solve symmetric linear systems with a factor of 2 speed up. We don't do most of this, we solve the most basic least squares problems. We don't do any of the QR with pivoting or SVD-based least squares. And we don't do any of the generalized least squares. That is something on the agenda. Some of it we may decide to leave out because divide and conquer is simply going to be superseded by our MR cubed algorithm. But in the meantime, these are the things that are missing. And the situation is even worse in the eigenvalue world. And so here are all of the eigenvalue problems: symmetric eigenvalue problem, nonsymmetric, SVD, generalized versions. And again, many things are missing from the parallel world. And we're asking ourselves which are the most important ones to do. So to some extent, this depends on feedback from the community, which are the most important ones to do first. There are some people who believe that this should all be automated, that you should write a code generator that will produce automatic code. And we have debates among ourselves and with that community. That's the part of the talk on software engineering, which, if time permits, I'll come to at the end. But let's just say that there's a lot of parallel code that is still not written. But more fun is to expand it to brand new functions, problems that we haven't solved before at all mathematically, either sequentially or in parallel. And so let me just say what some of those highlights are. Updating and downdating. What does that mean? That means that you've solved a system of linear equations, you've taken your matrix A and you factored it into L times U, and now you change your matrix just a little bit. You change one column, one row. You'd like to solve a new system of linear equations and do it for n squared instead of n cubed by changing your LU factorization a little bit. These algorithms have been around for a long time, but none of them have been optimized for memory hierarchies yet. And Pete Stewart at Maryland has signed up to do that. And so he will be producing a version of those to go out in the next release, not the next release, but a future release. Generalized singular value decomposition, that means the singular value decomposition of two matrices. I won't go into the details of the definition. There's one version of that in the original LAPACK code, but Xiaojun Bai at UC Davis has signed up to produce quite a few more that come up in other kinds of data analysis problems. And he also has much faster versions of the current Jacobi-based code in LAPACK. We have a few versions of Sylvester equation solvers in the current library. What's the Sylvester equation? AX plus XB equals C, where everything's a matrix. Okay, so you're solving for X, where X is a rectangular matrix. That comes up in control theory quite a bit, but there are more generalized versions of that, and our collaborators in Sweden are producing those. The one that I'm most interested in, and I will go in a little bit more detail, is a new n squared version of this MATLAB function, roots of p, finding roots of a polynomial. So let me say a little bit more about that one. So how does MATLAB, or most people perhaps, find roots of a polynomial? So what do? You have your polynomial coefficients. You put them in the top row of a matrix. You put ones below the diagonal. This matrix is now Hessenberg. And you say, please find the eigenvalues of that matrix using the standard eigenvalue problem. And the theorem is that the eigenvalues of that matrix are the roots of the polynomial. So this is an n-cubed algorithm. It's nice and stable. It's nice and reliable. So what does stable mean? That means it guarantees that you find exactly one copy of each root of a slightly different polynomial. That's the usual notion of numerical stability. Now, of course, order n squared algorithms go back a long ways. I mean, how old is Newton? These algorithms have been around for a long time, but none of them are stable and reliable in this sense. So how would you find all the roots using Newton? You'd find the first root. You'd deflate it, divide by the factor. Find the next one, divide by the factor, and so forth. And by the time you've divided out by enough of these factors, who knows what the polynomial has to do with the original polynomial you started with. So there's nothing stable and reliable about that at all. So here's the idea. So it turns out that if you look at this matrix and you look at any rectangle that's strictly above the diagonal, only the first row is non-zero. So obviously any such rectangle has rank 1. Now what happens if I start doing QR iteration, run the eigenvalue algorithm on this matrix? Well, it all fills in. All of these zeros above the diagonal fill in. But if you take any rectangle up there and ask what is its rank, the rank is at most 3. That's a mathematical property that's satisfied by that, and it's called semi-separability. And there's a huge literature on this semi-separable property. This is one example. So the idea is that we do not represent our data structure for representing this matrix is not a dense matrix anymore. It's a sparse matrix where we store 3 vectors for every upper rectangle in a certain sense. So the data structure is not an n squared object, it's an order n object. And when we run the algorithm, we don't operate on this, we operate on this sparse representation of order n data, and the complexity of one sweep of the QR algorithm goes from order n squared to order n, factor of n speed up, and the overall algorithm goes from n cubed to n squared. So we now have an algorithm which runs in the same speed asymptotically, big O sense, as Newton or any of these other reliable ones, and it has this same stability and reliability, we think. All right, so this was an open question for a while. A bunch of other people were working on it. I mean, many people have noticed the structure. People tried to make it stable. None of them could do it until recently. Minggu observed that here's the idea. We can make it stable in practice. What is the obstacle to stability? As we're running the algorithm, chasing the bulge, we have to maintain this rank 3 structure. And how is that done? It's by doing a little tiny 3x3 SVD or QR decomposition periodically to sort of compress things back down to rank 3. And we haven't seen it fail, but we haven't been able to prove it can't fail. So what goes wrong if it fails? The answer is, well, forget rank 3. Go to rank 4. Just maintain rank 4 throughout the entire algorithm. It's still order n squared. It works fine. So that is our proof in practice. Just by weakening that rank constraint, now it is a stable algorithm. And a lot of people have thought about this over time because it's sort of been a complicated subject. And this property of low rank up here is now very widely investigated in all sorts of things. You can think of, in fact, the fast multipole method this way as being a low rank off-diagonal matrix. So it's all related to that kind of material as well. Okay, so this has just added one more line. How do we prioritize all these things, right? Again, we have a very long to-do list. It kind of depends on what people want. And we're collecting input from the community as well as volunteers. You can see we have a lot of volunteers here at many places who are helping us produce this stuff. Okay, so our third goal, that was the end of the second goal, our third goal is automatic performance tuning. So I want to sort of have a little digression here and talk about what is automatic performance tuning. And this has become a hot topic. In fact, in the latest round of SciDAC proposals, which many of you participated in, there's a whole new institute, PERCS, which is one of its topics is how do you automate the process of tuning algorithms to fit in different architectures. Perhaps the most widely known one is Atlas, which I will say grew out of a project at Berkeley, which tunes the BLAs. And when it became possible to have tuned BLAs for every platform, that's what Cleve Moeller finally said, okay, now I can put LAPACK into MATLAB. That's why you all get to use LAPACK in MATLAB, because you don't have to buy the BLAs from anybody anymore. It's free. So FFTW is another famous one. It won the Simon Wilkinson Software Prize in, I think, '99. There's another big project which started out at Carnegie Mellon for doing this automatic tuning of signal processing algorithms for DSP chips. And I'm going to tell you a little bit about our own now sparse automatic tuning activity at Berkeley. So it's a little digression from dense linear algebra. It's called OSCE. So let me motivate tuning here. So when you tune dense matrix multiply, what do you do? What you're going to do is take your large matrix and break it up into little tiny blocks, smaller dense matrices, and multiply those. And put the pieces together to give you the product of the two larger matrices. And the tuning question is, what should the sizes of the small blocks be? Depending on the choices of those small block sizes, you get very, very different performance. So you have at least three parameters to pick. The dimensions of the three small, of the matrices in the small blocks. This picture shows a two-dimensional slice of that three-dimensional search space of the small block sizes. So here's the dimension of one size of the block, here's the dimension of the other size of the block, and then there's another dimension of size 1. This is for register blocking, so it's not worth thinking about algorithms that use more than 16 registers, right? Because this is a machine with 16 registers. So each one of these squares, a choice of n0, a choice of m0, represents an algorithm. So this is the search space of algorithms. And we're only searching ones that use 16 or fewer registers, so I'm only looking at these blocks. And all the blocks are color-coded by how many megaflops they ran at. So each one of these squares is an algorithm that we want to choose the fastest one. And here they all are, ranging from down to 100 megaflops here, up there, and there's the winner. It runs at 600 megaflops, and it's when you use 4 and 2. Why? I don't know. And I don't care anymore. I found it. That's the whole point of automatic performance tuning. This is going to be a different picture for every platform, and it's finding a needle in a haystack. It's a process we want to automate. It depends on the compiler, it depends on the hardware, it depends on the speculative execution in which instructions get generated. It's too complicated to model. It's different for every architecture. They change it every year in the architecture anyway, so you want to automate this process. So this is what we've been doing for BLAS for quite a while, and now I wanted to say how we've done this for sparse linear algebra. So let me talk about tuning sparse matrix vector multiply, SpMV. And here the blocking is a different kind of problem. We don't have large dense matrices to do anymore, but there's still a lot to be gained by optimizing how you what's the data structure for storing our sparse matrix and how should the inner loops be organized. So here is a large sparse matrix, Rafsky 3, it's from a standard database, it's some finite element problem, and I'd like to make y equals a times x run as fast as possible. So there's the usual dense loop. So let me zoom in on this upper corner and take a look at what the matrix looks like. And it turns out to be a lot of little dense 8x8 blocks because that's the size of the finite element discretization. So if I were to store this matrix in the usual format, I'd store each non-zero, wouldn't store any of the zeros. And for each non-zero entry, I'd store its column index, so I'd know where it fit in the matrix. And then I'd also have to store where each row began and ended. And the loop in the standard sparse linear algebra framework would be a loop over each row and accumulate the product. There's the matrix entry, there's the x, and there's my index I have to keep around of which column does that matrix entry lie in. So this is called the CSR format. But if you look at this, you can see, gee, this is a very, very regular matrix. I have 8x8 blocks. So if I know where the upper corner of this block is, if I know which row and which column it's in, I don't have to store 64 indices for all the other matrix entries. I can just store one and compute all the others because I know ahead of time it's 8x8 blocks. And so in fact, I can make my data structure for the indices 64 times smaller than it was before. I can decrease the memory traffic by a factor of 64, and that ought to give me some speed up, right? So that's sort of a perfectly natural thing to do that people have tried. And so let me try that. I'll show you in the next slide how much faster it is. But let me point out that if this is an 8x8 block, I can store it as a single dense 8x8 block, certainly. But I could also store it as two 8x4 blocks, or four 4x4 blocks, or there's all sorts of possibilities, right? In fact, there's 16 different ways I could store this without, I could store it with 1, 2, 4, 8 row blocks, or 1, 2, 4, 8 column blocks. So there's 16 different algorithms here. That's my search space. Let's see what happens. So here, I have 16 squares. Each one represents an algorithm. So there's the traditional algorithm storing it as a 1x1 block. There's the algorithm storing it as an 8x8 block. There it is storing it as a bunch of 2x4 blocks, all the different 16 possibilities. And again, it's color-coded by megaflop rate. And the numbers are speed up. So this is the unoptimized algorithm that runs at speed 1. If I do my 8x8 blocks, I get a big win. It's 1.55 times faster. I should be happy. But the best thing to do is to store it as 4x2 blocks, and I get 4 times faster. Why? Again, it depends on all the vagaries of the compiler and, and instruction prefetching and everything else. And we don't know why, but 4 is the winner, and we will use it. And that is the process that we automate. So this is a picture that we collect offline in a tuning process for every sparse matrix. In fact, not just for 1, 2, 4, and 8. We do all possible block sizes. And we store this in a template so that at runtime we can quickly decide what to do. So this is what the picture looks like for some Itanium 2. There's the winner. Here are the same pictures for a bunch of other platforms. Every machine is different. This is why we have to do tuning. The sweet spot is here, 8x8 wins, 8x8 wins, either 8x2 or 4x4 wins. There it's 8x8. And different platforms look different. Even the same, so here's 2 different Itaniums, they all look different. This is data we have to collect offline. It's not something that we want to analyze every time a new compiler, a new piece of hardware comes out. This is a process that should be automated. Okay, so let me say another reason why this is an interesting process. So here's another thing that we want to automate in the tuning process. So here's a matrix which doesn't have quite as simple a nice 8x8 block structure as the last one did. In fact, the best you can do by kind of eyeballing it is it sort of seems to have a 3x3 block structure. But if you actually were to store it as 3x3 blocks, you would end up filling in a lot of these zeros with non-zeros. So in fact, all the red ones are things that are zeros you would store explicitly and do explicit arithmetic with. In fact, you add 50% to the data structure. This seems like a terrible idea. You're growing the data structure by 50%, and you're doing all this arithmetic on zeros, and it turns out to be a great idea. It makes the whole thing run in 1.5 times faster. Why is that? Because the megaflop rate goes up by a factor of 2.25. So I'm doing 50% more work, but I'm doing it 2.2 times faster, and the whole thing turns out to be 1.5. This is not something that you would see by eyeballing it. It's something you get by measuring, and it's an empirical sort of discovery that's made at runtime when we do this tuning. So here the best thing to do is 3x3 blocking out of all the possibilities. Here's one more example that comes up in tuning. And in particular in the BiCG algorithm, which is a standard Krylov subspace method. If you look at the inner loop, it spends half its time doing A times X, and the other half of its time doing A transpose times Y. So what do? How do we tune it? Well, if you use 3x1 blocking for the matrix, then you get these megaflop rates. AX works really well. It goes at a gigaflop. But A transpose Y is a lot slower. If you try 3x3 blocks, then they're both pretty fast, but neither one is anywhere close to a gigaflop. So here's the idea. I'm not going to tune AX and A transpose Y. I'm going to do both of these at the same time. I'm going to have a single operation where my inner loop is accumulating both of these simultaneously. So the idea is you read in a block of your matrix A, and you use it twice, once to accumulate a bit of AX and once to accumulate a bit of A transpose Y. So the amount of memory traffic goes down by a factor of 2. You read A from memory once, and you do twice as much work, and it turns out the winner is 3x3 blocks, and it runs at 1.4 gigaflops. So this is another level of tuning. You have to go one level up in the algorithm and realize that this is what you should be tuning, not a single operation. So we have a whole library that does this. It's called OSCE, which stands for Optimized Sparse Kernel Interface. I've only talked about this one optimization so far, which is register blocking, which got us up to a factor of 4. You also have the option of splitting your matrix into 2 parts. If you're doing finite elements, maybe you have 4x4 blocks and 6x6 blocks because you have a mixed finite element problem. You should rate your matrix in 2 different data structures. That gives you a factor of 1.8 more over what we just got. Maybe your matrix is best stored by diagonals. You can get a factor of 2 over that. Maybe you should run the traveling salesman algorithm to try to reorder the rows and columns to create dense blocks where they weren't there before. That gives you another factor of 2. If your matrix is symmetric, you only you can do that particular optimization. That gets you another factor of 2.6. If your matrix is really huge, you should break it up into cache size blocks. There's another factor of 3. If you have multiple vectors, then of course you do all those at the same time. There's a factor of 7. So you can have arbitrary combinations of those. All of these are built into our tuning library. Sparse triangular solve, there's a factor of 1.8 for doing the tuning. And as I said, instead of just doing a single operation, maybe if you look at your algorithm, you're really doing A transpose times X. That's what you should be tuning for. There's factors of 4 available there. So all of this is available as a standalone library, or it's been integrated into PETSI. So you can call this from PETSI, and there's an interface which will say, please tune my matrix, or you can say, just please do it automatically. And if you wonder where the name OSCE comes from, then it also happens to be the name of the Cal football mascot there. His name is OSCE. So we also do football at Berkeley. So, so let me go on here. Okay, so that was sort of an excursion into performance tuning for sparse matrices. So what is the performance tuning agenda going back now to LAPACK and ScaLAPACK? And it turns out that there are 1,300 tuning parameters we've never tuned. They've been in there for a very long time. They're in a table in a subroutine call, and they're throughout the library, and we just put in some numbers like 32 and 64 in the hopes of someday going back and tuning them to increase performance. Well, it's time to go back and tune it. And we have to automate it because there's no way we can do this by hand anymore. So what we'd like to do is extend all these techniques I've talked about to tune all these different parameters. And I'll just talk about one particular one, which is, we think, probably the biggest win, which is converting the data layouts, which are used in parallel on the fly, so that the user can use a really, really simple layout, which is terrible for performance. We'll completely change the layout under the user's nose without the user knowing about it, solve it in the fast layout, and then convert back on the way out. So let me explain why that's a good idea. So here are the ScaLAPACK data layouts. So imagine I have a matrix here shown as a square on 4 processors. What are the different ways you could spread that matrix out over 4 processors? You could store it in column blocks and row blocks analogously. So processor 0 gets that part, and so on and so forth. You could do it in a cyclic pattern. You could do it in this block cyclic pattern, or you could do it in this really hairy-looking 2D block cyclic pattern. Users don't like this. Users like this. This is a natural way to lay out a matrix. But this is terrible for performance, and this is great for performance. So let me just say why. Suppose you're doing Gaussian elimination, which is your sort of standard operation. what do? I take my matrix and I update the trailing submatrix, this big square down here, and I keep marching my way along. So at any particular point in the algorithm, I'm updating, I'm doing all my work in a square that fits down in this lower right corner. So that by the time I get down here, processors 0 and 1 are completely idle. There's no parallelism there anymore at all. So this problem fixes that. I've divided up the work so that any of these trailing squares now is evenly divided. There's load balancing. But I can't do BLAS3 anymore because it's all column based, right? There's no BLAS. So here I can kind of split the difference. Here I have reasonable load balancing down here. 4 processors own this trailing square. And I kind of have load balance, and I kind of have BLAS3 because there are enough columns in there to get a BLAS3 call. But now I have a different bottleneck because I have to do an LU decomposition of this tall skinny bit, and there's no parallelism there whatsoever. So when you finally say, how do I get perfect load balance and parallelism, you get something that looks like this. So now, no matter which trailing square I pick, it's evenly, every processor owns a quarter of it, so it's perfectly load balanced. And if I look at any column or any row, I have parallelism in it. So this is the right layout, but users hate it. Okay. So the idea is the user will give us this, or whatever the user wants. We will run a performance model, do some automatic tuning, say, is it worth converting to something like this? How much time does it take to convert? How much faster is this? Convert it, solve it here, convert back. So here's one example of the payoff. And there's a factor of 8 payoff for doing this in just one particular example. So this is LU on a problem of size anywhere from 1,000 to 10,000 on a 60 processor machine. And you could do it anywhere from a 1x60 layout, that's the bad one, to a 6x10. That's the good layout, the 2D block cyclic layout. And this is seconds versus problem size. And so it's a little hard to see down here. But here you can see the 1x60 layout is several times slower than the 6x10 layout. And in fact, the speed up ranges from a factor of 2 to a factor of 8 by changing the data structure. How much does it cost to redistribute the data structure? An extra 1 to 10%. So it's clearly worth doing this. And this is part of the tuning that we want to accomplish. OK, so that's all I wanted to say about sort of practical matters of dense linear algebra. And I now want to finish by saying a little bit about group representation theory, which is actually also dense, has to do with dense linear algebra. So I mentioned earlier in the talk that there is now this possibility that matrix multiply will become an order n squared algorithm. I'd like to say a little bit about this very recent work by these guys and what our contribution is. So let me talk by analogy to the FFT and say why you can think about speeding up matrix multiply as like it's the same as speeding up the FFT. So we all know how to multiply polynomials quickly, right? You take the polynomials, you evaluate them at the roots of unity using the FFT, you multiply their values of the roots of unity, and then you do the inverse FFT to get the coefficients back. Here's a fancier way to look at exactly the same algorithm. I'm going to take my polynomial, call it P, I'm going to map it into a group algebra. That's a linear combination where the coefficients of the polynomial are the coefficients of the polynomial. And the group algebra is just the entries of a cyclic group, roots of unity. We represent them by roots of unity. Then what do? We multiply in the group algebra, and then we extract out the coefficients using the inverse FFT. So this is fancy language for what we teach sophomores, okay? So the same idea works with matrix multiply, except we can't use abelian groups anymore. We need to use non-abelian groups with a particular property. So here's the idea. I'm going to find a group, G, and it has to have 3 subsets with the property that if I take a product of 3 entries, little x and big X, little y and big Y, little z and big Z, and their product is the identity in the group, then the only way that can happen is if these are all simultaneously the identity in the group. So now, defining that, I can give you a mapping from a matrix to a group algebra entry. I'm going to sum over all the entries of the matrix, and I'm going to index them by entries of the group. So this is a coefficient times a group entry, x inverse times y. This kind of looks like a quadratic form, but now this is a group entry, and this is a perfectly formal operation. There's no floating point here. It's kind of like a data structure operation. I'm representing my matrix as a single entry in a group algebra. And I'll do the same thing. So I'll map A to this. I'll map B to this. So now it turns out that if you just do the usual matrix multiply operation, this is preserved under the group algebra. You get the same entries as you'd get as if you multiplied the matrices and formed its representation. So it's just like FFTs. And so it turns out that the search for fast algorithms for matrix multiply doing this is reduced to the search for groups with certain properties. And so far, they've found an algorithm that beats, that equals the world's record. The world's record is currently Coppersmith and Winograd. It's about end of the 2.38, and they found a group that matches. Okay. So this is a really brief tour, and this is where the group representation theory comes in. So if you write down the algorithm at a really high level, this is what it looks like. It's recursive. So you take your matrices A and B and you embed them in the group algebra by doing this formal sum. This is an exact operation. It's kind of like a data structure manipulation. There's no floating point. Then to do the recursion, it turns out it is a real, honest-to-God floating point FFT. So and there's some round off involved there, which I'm going to analyze in a second. So then you reorganize the results into new matrices that are smaller, and you have to multiply them. So it's going to reduce large matrix multiply into small matrix multiply. You multiply these new matrices recursively by calling the same algorithm. You get some round off. You take the output, reorganize it, produce inverse FFTs, and extract the coefficients. So this is at a very high level what this recursive algorithm looks like. It has some flavor of Strawson, but you can see it's not really quite the same as Strawson. So this was discovered a few years ago. People are now searching for the right groups. Let me tell you what our contribution is, then I'll finish. We proved that all these algorithms are numerically stable. So the theorem says that any algorithm of this class is numerically stable in the same sense that Strawson is. That the difference between the true product and the computed product is, machine epsilon times some modest constants times norm A times norm B. And so this is exactly the same kind of bound that you'd get from Strawson. And in fact, you can prove something even stronger. So we don't know what the fastest algorithm is yet for matrix multiply. But let's suppose it's n to the omega for some omega. Finding omega is a big question. But let's suppose we knew what it was. The theorem says that no matter what omega is, we can find an algorithm whose complexity is almost as good that's numerically stable. So whatever the best algorithm is, it can be modified just slightly to be numerically stable in this sense. So all the fast algorithms in the world that you can imagine are now numerically stable. And now, is this practical? I think n would have to be astronomically large for this to be of great interest, but nonetheless, it's nice to know that they're numerically stable. So let me now close. This is my last slide. There's lots to do in dense linear algebra. I've talked about new numerical algorithms, architectural challenges. There's lots of things in software engineering I haven't even touched on. And we have support, but a lot of it depends on our very generous colleagues in many countries who are contributing software. And thank you very much. That's the end of my talk.
We have time for a question.
So about the tuning parameters.
Excuse me?
The tuning parameters.
Yes,
so
yes.
I think from what you said, it's mostly blocking.
Mostly block.
Right? These are the main two categories.
Those are most of them. That's right.
How about, if you look at, for example, compiler options like these?
Oh, that's
Zillions of options.
so that is another level of tuning, and we do pursue that as well, so that when we take our kernel that we produce with a particular set of block sizes, we also want to try all the compiler options. In fact, we can try all the compilers and then link that in. And so that's yet another level of tuning that yes. And sometimes the 05 or whatever it is not the right thing to use, as I'm sure people in this audience know. And so that's a part of the tuning process that has to happen as well. So,
have you seen any potential? What kind of performance variation have you observed?
So there's a chapter on that in a student's thesis of mine, Rich Vudak. And the actual numbers I can't remember where it depends on the compiler. But let me say that there's one big compiler opportunity we've not pursued here. And let me back up. All right, let me go this way. Okay, let me look at these. So all these kind of irregular pictures, what do the inner loops look like in this case? So each of these comes from completely unrolling an inner 8x1 block or 4x2 block or 4x4 block. So it's completely unrolled. And it may be that that's the wrong thing to do. We've never done any Atlas or FPAC style tuning on these particular kernels. And so it could well be that by using, for example, a different kind of unrolling, let me back up one more slide. Back up one more. It could be that we could raise this 1.55 to 4.07 by reorganizing the 8x8 block to be internally doing 4x2 blocks by using a larger search space, right? So we haven't really tuned over all these possibilities. We simply say, okay, 4 by 2 wins. So, but we may be able to make these pictures more regular by saying that any multiple of 4 by 2 would also run at this speed by doing a better job on the compiler level. But we haven't had time to do that yet. That's certainly been on our to-do list for a while, but we haven't done it. So another area where this kind of tuning happens is with stencil operations. So if you look inside multigrid, for example, in the smoother, then a lot of the time is spent in a sparse matrix operation with a particular constant stencil that's the same at every mesh point. And that's a completely different kind of tuning operation, and we've been working on that as well too and trying to get that into compilers. Yes?
In your algorithm, you mostly try to exploit, or at least in some of the algorithms, to exploit the condition of the matrix, the condition number.
Right, right.
What is sacred about the matrix? Why not simply look at the eigenstructure of the matrix, or perhaps a block low rank representation of the matrix, or something to that effect, and store those low rank blocks and do all of the math on those?
That's exactly what's done in the case of the polynomial system solver. So there's sort of two worlds. One is the dense world, and the other one is which using direct methods. The other one is the sparse iterative world, where you have a huge range of preconditioners to try, or approximate sparse matrix vector multiplies to try that I know some of you folks here have done. Within the dense world, we're perfectly happy to use different data representations, but we want to have a certain guaranteed accuracy at the end. And if we're doing something iterative, then we have to, at some point, we have to have the original problem stored so that we can compute a residual or some way guarantee that the answer is converging to epsilon.
Is it really that difficult to look at the eigenstructure and get down to machine precision and just hold on to all of the singular vectors?
Oh, okay. So that's an interesting question. So, and I have a whole nother talk on it, in fact, which I won't inflict on you. So the question is, what properties does your matrix have to have in order for you to be able to guarantee the kind of accuracy that you want? It turns out the matrix has to have a fairly special structure. And there are certain matrices for which we've worked that out in some detail. The first one for which it was figured out and was a bidiagonal matrix. And that is actually the core of the general singular value problem. You take a dense, you make it bidiagonal. It turns out you can find all the singular values, all the bits, they're all right, and it doesn't cost you anything extra. But for the vectors, there's still a condition number there which says that you can't expect to get some of them accurately. It depends on the distance between the singular values. But there's a whole class of those, and as I have a whole table of which ones we can and can't do. And some of those are going into LAPACK, but some of them are just perhaps too specialized. Let me tell you the latest progress in that area, just sort of one example. You can take an elliptic PDE, scalar elliptic PDE on an arbitrary triangular mesh with an arbitrary coefficient function, can be as wild as you want, and you want to find its eigenvalues. We can do that and get every eigenvalue to guaranteed high relative accuracy using a new decomposition of elliptic PDE. So for that problem, we have to deeply exploit properties of elliptic PDE, and we get a new algorithm. But the next problem is going to have another property. We're actually trying to come up with a decision procedure. Given the structure, can you write, in the Turing sense, a decision procedure to decide if the structure will permit high relative accuracy? And we have some results in that direction, but we haven't completely figured it out yet.
Okay, let's thank our speaker.